Good evening, everyone. Welcome to One Concept Per Day. And this is your question number 2. In question number 1, we had already seen about how interference pattern takes place. And we have seen about, what will happen if the laser light is being replaced by a tungsten filament, which gives you a definition of what is meant by coherence. If you have coherence, then definitely you will be able to get a sustained interference pattern. Otherwise, the pattern will change. We have seen this in the previous video. And then we have seen about how does the intensity pattern looks in case of a single slit diffraction and a double slit interference pattern. You see, in a double slit interference pattern, you get a bright and dark fringes, which are equispaced, and the intensity of this, all the bright fringes are seen to be the same. But in case of a diffraction pattern, you see the central fringe will have a larger intensity, but while the adjacent fringes will have a lesser intensity. That's what we have seen, the difference between these two. And then we have also seen about how to calculate the value of the distance between the two slits, using what is the wavelength and what you mean by the angular separation between the two fringes. And after that, we also looked into, so what will happen if electrons are used. We connected this one with the quantum mechanical part, which is the de Broglie wavelength. And then now we are looking into the second part of it. Now let us read the problem. The diagram below shows the experimental arrangement by observing Fraunhofer diffraction by a single slit. Fraunhofer diffraction is a type of diffraction. This question is also taken from 2003 May paper. So after passing through the convex lens L1, which is the lens L1, this is the lens L1. After passing through the convex lens L1, the monochromatic light from a point source P is incident on a narrow rectangular single slit. So it is now incident on the single slit over here. And then what else does it being given? After passing through this, lens is brought to a focus on this lens by L2. So now after passing through the lens L2, it comes to screen over here. Then the point source P is at the focal point of the lens L1. So this is very, very important. There are two things which are very important here. First is monochromatic light. That means what? A single wavelength. Maybe like an LO source or a laser source or anything like this. The point P is the focal point of the lens. This is the focal point. Which means what? Which means any ray that passes through the focal point, what will happen? After refraction, it will be rendered parallel to the principal axis. Like this, it will be rendered parallel to the principal axis. Now what happens in this case now? See, this ray goes here, gets reflected back. So or maybe get absorbed here because there's no way it can go like this. So therefore, let me draw one more ray here. I'll draw one more ray here. So this will go like this over here, and maybe this will go like this over here, and will be incident parallel to this lens. And this will also, I'll put one more ray like this, and then sorry, not here. I'll put one more ray here, and then this will now pass like this over here. It comes like this over here. Now these two are the two rays, which are kept parallel. Now as a result of it, what will happen? Now this will now get refracted here. Now let us read the problem. Where does it fall? It says after passing through the light, the slits, light is brought to a focus on the screen by the lens L2. Now you are going to bring these two beams of rays to a point at L2 by the lens L2. These are collimated, and then this ray is made to be focused at this point, and this ray after refraction also gets focused at this point over here. Now this is what we have got over here. Right, let us draw the ray diagram first to understand the rest of them. Then what happens? The point X is on the screen is directly opposite to the central point of the slit. So that's all fine. So maybe slight deviation I have made. If I use a scale, probably I would have got a correct one. Then explain qualitatively how Huygens principle accounts for the phenomena of single slit diffraction. So how do you get a single slit diffraction? So what do you write here? You should write that each point on the slit acts as a source of secondary wavefronts. Secondary wavefronts is the first point. There are 2 marks over here. This is the first point. And then the second point is that interference of these wavefronts on the screen gives rise to fringes. right? So this is what happens. This is nothing but the principle of diffraction, right? In interference, what happens? You have two waves, okay, which is being which joins together or which interferes to form an interference pattern on the slit. Okay, here what happens? You have only one slit, so different parts of the same wave join together to give this one interference. Both the cases it's only interference, okay, but only thing is, since it is single slit, we call it as diffraction. If it is multiple slit, that is two slit, we call it as an interference. While when you consider, for example, a grating, what do you call this grating as? A grating has multiple slits over here, multiple slits. Is it diffraction or interference? Again, we call this as interference, or we call this as a diffraction grating. The phenomena that's happening here is interference, but what is happening finally, okay, what is happening over here? The rays actually bend together, and thus you see you get a diffraction. Though it's a misnomer, you can say it's a diffraction grating. Many slits are there. The light falls onto one of these slits or multiple slits, and then you get an interference pattern. Okay, now we have mentioned this for 2 marks. Then next, use the axis below, draw a graph on the to show how the intensity of the pattern varies with distance along the screen. The point X on the screen is to be shown as a reference point. This is a sketch graph. You need not add any numerical values. And this is for 3 marks. Okay, the question is very similar to what we have seen in the earlier one. Anyway, I will repeat this once again here. So this is for a single slit diffraction. Remember, it's not for interference. So what will happen? At the point X, you will get a maximum. Okay, and this should be symmetrical here. And after that, what happens? You should have one minima here, one maxima, secondary maxima here, and one more maxima here. Okay, and this keeps on going if I keep on writing it. Now here, once again, I get one maxima here, and then one more maxima here. See to it while you write it, okay, this will carry you 1 mark, okay, which tells you that the maxima is being seen here. Okay, at the point X, it should be exactly at this point. Okay, we have seen this. Maybe you can draw a line and then say, okay, it's exactly at this point. Secondly, the peaks of these two should be the same. Okay, and lastly, see, make this much more smaller. Don't make it this much larger. Make this much more smaller like this. Okay, this will carry 1 more mark. Okay, and then these peaks should be smaller. This peak should be smaller, and the distance between these peaks, this minima here, should be the same. This, if it is beta, this should also be beta. While this should be 2 times beta. Then it should be larger. There should be a fatter curve and should be a thinner curve. Okay, and here also is always it is beta, and here it is beta. Okay, if you do this one, you get 1 more mark over here. So 3 marks. First one was central maxima, second one for the secondary and the tertiary maxima that you are going to write, and lastly 1 more mark for the distance between the peaks where it hits the x-axis. Okay, the middle one should have 2 beta, the rest of them should have only beta. Okay, this is what you need to write. Okay, next. In the experiment, the light has a wavelength of 500 nanometers. Lambda is given over here. The width of the central maxima of the screen is 10 millimeter. Width of the central maxima, which is given here. This value is given. Width of the central maxima is seen to be 10 millimeter. Okay, 10 millimeter. When light of the known wavelength lambda is used, the width of central maxima is 13 millimeter. Now you have, let me write it down here. When lambda 1 was seen to be 500 nanometer, the value of D1 was seen to be 10 millimeter. And when light of unknown wavelength lambda is used, when I do not know the value of lambda, then the value of D2, the width of the central maxima intensity, was seen to be 13 millimeter. 13 millimeter. Hey, I'm sorry, this is not D1 and D2. This I should write this as beta 1 and beta 2. Okay, that's what I should write. Now, we'll determine the value of lambda. So, how do I write? We know that beta is equal to lambda capital D divided by small d. This capital D and small d I am not going to change. The distance between the screen, okay, I am not going to change. And what is being seen, the small d also I am not going to change. Okay, so only the value of lambda is being changed. So, what should I do? So, therefore, I can now say beta proportional to lambda, right? When lambda increases, beta increases. Now, the question is simple. I will do beta 2 divided by beta 1 is equal to lambda 2 divided by lambda 1, because lambda 2 is a subject. I need to know this. So, what is beta 2? Beta 2 is 13. So, 13 millimeter divided by 10 millimeter. is equal to lambda 2 divided by what's lambda 1? Lambda 1 is 500 nanometer. There's a reason for why I write the units, because at the end, if you do not know the units, you lose a mark. So it's better always you write the units. This millimeter goes away, you get this as 1.3. 1.3 is equal to lambda 2 divided by 500 nanometer. Our lambda 2 should be 1.3 multiplied by 500 nanometer, which should be, I should be getting this as 650 nanometers. With value of lambda, value lambda is equal to 650 nanometers. Okay, next. The lens L1 is now removed and another point source Q emitting light of the same wavelength as P is placed 50 millimeter. Now what I am going to do, earlier there was a lens here. Okay, there was a lens over here. Okay, now what I am going to do, I am going to remove this. Let me remove this. Let me not put it over here. Okay, and another point source Q is placed over here of the same wavelength as P, and okay, as shown over here, right? And now what has been asked? Distance between the source and slit in this D is 1.5 meter. So let us write down all what has been given to you. This is B over here, this is D here, this value is D, this value is capital D, this value is capital D. Okay, and then state the condition for the image of P and the image of Q formed on the screen to be just as okay. So this question is not there currently from your syllabus. Okay, so this resolution of two images has been completely removed. Okay, but still if you want to do it, then okay, we will definitely go ahead and we'll proceed with this. Okay, now state the condition. Okay, this is called as a Rayleigh's condition. What is a Rayleigh's condition for just resolving two images? Okay, so maybe in future it could be useful, this question. So this is about the image, the first minimum of one image should be equal to the first maximum. I should not write equal to, you should say it should be overlapped. If it overlaps with the first maximum of the second image, then we can say the image, say the points P and Q are completely resolved, right? So that is what is the condition. This is called as the Rayleigh's criteria. Okay, image of point Q is completely resolved. Okay, next step. Determine the minimum width B of the slit for the two images to be just resolved. So now what we do is, there is a formula for this which will tell you lambda by B is equal to small d by capital D. This also you don't have in your syllabus. Okay, this was for your 2016 to 2024 students, so they had this anyway. So I am doing this one here. Now as a result of it, what is the value of what is that we need? Lambda value. What's the value of lambda? 500 nanometers. Nanometers divided by what's the value of B? I need to find out the value of B. Which is equal to small d by capital D. What's the value of small d? 5 millimeter. This is 1.5 millimeters. 5 millimeter divided by 1.5 meters. So by doing this, I get this 5 and this 5 cancels. So I can now write 100 nanometer is equal to divided by B, because I have 1 here, right? 100 nanometer is equal to 1 millimeter divided by 1.5 meters. Okay, now let me solve this. So I will use a unitary method, or I'll just do cross multiplication. I can now say B is equal to 100 nanometers multiplied by 1.5 meters divided by 1 millimeter, which should now be equal to, how much is it? This is 1.5 into 10 to the power of 2 into 10 to the power of minus 9 divided by 10 to the power of minus 2. How much will this give me? Value of B here would be 1.5 into 10 square, 10 power 2 minus 9, 10 power minus 7. Then write down 10 power minus 7, minus 3 goes upwards, plus 3. So this should be equal to 1.5 into 10 to the power of minus 4. What is this B here? This is meter. Okay, or I can now write this as 0.15 millimeter. B is equal to 0.15 millimeter. Okay, so thus we have come to an end to today's test paper, and tomorrow we'll see a new one. Thank you. So before you leave, do share these videos and subscribe to my channel for more updates. So YouTube algorithm will also recognize if you like my videos more, if you really like it. Thank you for your kind patience watching. Thank you.